Hello, and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about linear regression, aka General Linear Models Part 1. There's a lot of parts to linear models, but it's a really cool and powerful concept, so let's get right down to it. I promise you, I have lots and lots of slides that talk about all the nitty-gritty details behind linear regression. But first, let's talk about the main ideas behind it. The first thing you do in linear regression is use least squares to fit a line to the data. The second thing you do is calculate R squared. Lastly, calculate a p-value for R squared. There are lots of other little things that come up along the way, but these are the three most important concepts behind linear regression. In the StatQuest, fitting a line to data, we talked about fitting a line to data. Duh. But let's do a quick review. I'm going to introduce some new terminology in this part of the video, so it's worth watching even if you've already seen the earlier StatQuest. That said, if you need more details, check that StatQuest out. For this review, we're going to be talking about a data set where we took a bunch of mice and we measured their size and we measured their weight. Our goal is to use mouse weight as a way to predict mouse size. First, draw a line through the data. Second, measure the distance from the line to the data. Square each distance and then add them up. Terminology alert. The distance from the line to the data point is called a residual. Third, rotate the line a little bit. With the new line, measure the residuals, square them, and then sum up the squares. Now rotate the line a little bit more. Sum up the squared residuals, etc., etc., etc. We rotate and then sum up the squared residuals. Rotate, then sum up the squared residuals. Just keep doing that. After a bunch of rotations, you can plot the sum of squared residuals and corresponding rotation. So in this graph, we have the sum of squared residuals on the y-axis and the different rotations on the x-axis. Lastly, you find the rotation that has the least sum of squares. More details about how this is actually done in practice are provided in the StatQuest on fitting a line to data. So, we see that this rotation is the one with the least squares, so it will be the one to fit to the data. This is our least squares rotation superimposed on the original data. Bam! Now we know why the method for fitting a line is called least squares. Now we have fit a line to the data. This is awesome! Here's the equation for the line. Least squares estimated two parameters: a y-axis intercept and a slope. Since the slope is not zero, it means that knowing a mouse's weight will help us make a guess about that mouse's size. How good is that guess? Calculating R squared is the first step in determining how good that guess will be. The StatQuest R squared explained talks about, you got it, R squared. Let's do a quick review. I'm also going to introduce some additional terminology, so it's worth watching this part of the video even if you've seen the original StatQuest on R squared. First, calculate the average mouse size. Okay, I've just shifted all the data points to the y-axis to emphasize that, at this point, we are only interested in mouse size. Here, I've drawn a black line to show the average mouse size. Bam! Now, sum the squared residuals. Just like in least squares, we measure the distance from the mean to the data point and square it, and then add those squares together. Terminology alert. We'll call this SS mean. For sum of squares around the mean. Note, the sum of squares around the mean equals the data minus the mean squared. The variation around the mean equals the data minus the mean squared divided by n. N is the sample size. In this case, n equals 9. The shorthand notation is the variation around the mean equals the sum of squares around the mean divided by n, the sample size. Another way to think about variance is as the average sum of squares per mouse. Now go back to the original plot and sum up the squared residuals around our least squares fit. We'll call this SS fit for the sum of squares around the least squares fit. The sum of squares around the least squares fit is the sum of the distances between the data and the line squared. Just like with the mean, the variance around the fit is the distance between the line and the data squared divided by n, the sample size. The shorthand is the variation around the fitted line equals the sum of squares around the fitted line divided by n, the sample size. Again, we can think of the variation around the fit as the average of the sum of squares around the fit for each mouse. In general, the variance of something equals the sum of squares divided by the number of those things. In other words, it's an average of sum of squares. I mention this because it's going to come in handy in a little bit, so keep it in the back of your mind. Okay, let's step back a little bit. This is the raw variation in mouse size. And this is the variation around the least squares line. There's less variation around the line that we fit by least squares. That is to say, the residuals are smaller. As a result, we say that some of the variation in mouse size is explained by taking mouse weight into account. In other words, heavier mice are bigger, lighter mice are smaller. R squared tells us how much of the variation in mouse size can be explained by taking mouse weight into account. This is the formula for R squared. It's the variation around the mean minus the variation around the fit divided by the variation around the mean. Let's look at an example. In this example, the variation around the mean equals 11.1 and the variation around the fit equals 4.4. So we plug those numbers into the equation. The result is that R squared equals 0.6. which is the same thing as saying 60%. This means there is a 60% reduction in the variance when we take the mouse weight into account. Alternatively, we can say that mouse weight explains 60% of the variation in mouse size. We can also use the sum of squares to make the same calculation. This is because when we're talking about variation, everything's divided by n, the sample size. Since everything's scaled by n, we can pull that term out and just use the raw sum of squares. In this case, the sum of squares around the mean equals 100, and the sum of squares around the fit equals 40. Plugging those numbers into the equation gives us the same value we had before. R squared equals 0.6, which equals 60%. 60% of the sums of squares of the mouse size can be explained by mouse weight. Here's another example. We're also going to go back to using variation in the calculation, since that's more common. In this case, knowing mouse weight means you can make a perfect prediction of mouse size. The variation around the mean is the same as it was before, 11.1. But now the variation around the fitted line equals 0 because there are no residuals. Plugging the numbers in gives us an R squared equal to 1, which equals 100%. In this case, mouse weight explains 100% of the variation in mouse size. Okay, one last example. In this case, knowing mouse weight doesn't help us predict mouse size. If someone tells us they have a heavy mouse, well, that mouse could either be small or large with equal probability. Similarly, if someone said they had a light mouse, well, again, we wouldn't know if it was a big mouse or a small mouse because each of those options is equally likely. Just like the other two examples, the variation around the mean is equal 11.1. However, in this case, the variation around the fit is also equal 11.1. So we plug those numbers in and we get R squared equals 0, which equals 0%. In this case, mouse weight doesn't explain any of the variation around the mean. When calculating the sum of squares around the mean, we collapse the points onto the y-axis just to emphasize the fact that we were ignoring mouse weight. But we could just as easily draw a line, y equals the mean mouse size, and calculate the sum of squares around the mean around that. In this example, we applied R squared to a simple equation for a line, y equals 0.1 plus 0.78 times x. This gave us an R squared of 60%, meaning 60% of the variation in mouse size could be explained by mouse weight. But the concept applies to any equation, no matter how complicated. First, you measure, square, and sum the distance from the data to the mean, then measure, square, and sum the distance from the data to the complicated equation. Once you've got those two sums of squares, just plug them in and you've got R squared. Let's look at a slightly more complicated example. Imagine we wanted to know if mouse weight and tail length did a good job predicting the length of the mouse's body. So we measure a bunch of mice. To plot this data, we need a three-dimensional graph. We want to know how well weight and tail length predict body length. The first mouse we measured had weight equals 2.1, tail length equals 1.3, and body length equals 2.5. So that's how we plot this data on this 3D graph. Here's all the data in the graph. The larger circles are points that are closer to us and represent mice that have shorter tails. The smaller circles are points that are further from us and represent mice with longer tails. Now we do a least squares fit. Since we have the extra term in the equation representing an extra dimension, we fit a plane instead of a line. Here's the equation for the plane. The y value represents body length. Least squares estimates 3 different parameters. The first is the y-intercept. That's when both tail length and mouse weight are equal to 0. The second parameter, 0.7, is for the mouse weight. The last term, 0.5, is for the tail length. If we know a mouse's weight and tail length, we can use the equation to guess the body length. For example, given the weight and tail length for this mouse, the equation predicts this body length. Just like before, we can measure the residuals, square them, and then add them up to calculate r squared. Now, if the tail length, or the z-axis, is useless and doesn't make the sum of squares fit any smaller, then least squares will ignore it by making that parameter equal to 0. In this case, plugging the tail length into the equation would have no effect on predicting the mouse size. This means equations with more parameters will never make the sum of squares around the fit worse than equations with fewer parameters. In other words, this equation, mouse size equals 0.3 plus mouse weight plus flip of a coin plus favorite color plus astrological sign plus extra stuff, will never perform worse than this equation, mouse size equals 0.3 plus mouse weight. This is because least squares will cause any term that makes sum of squares around the fit worse to be multiplied by 0 and, in a sense, no longer exist. Now, due to random chance, there is a small probability that the small mice in the dataset might get heads more frequently than large mice. If this happened, then we'd get a smaller sum of squares fit and a better r squared. Wah wah. Here's the frowny face of sad times. The more silly parameters we add to the equation, the more opportunities we have for random events to reduce sum of squares fit and result in a better r squared. Thus, people report an adjusted r squared value that, in essence, scales r squared by the number of parameters. R squared is awesome, but it's missing something. What if all we had were 2 measurements? We'd calculate the sum of squares around the mean. In this case, that would be 10. Then we'd calculate the sum of squares around the fit, which equals 0. The sum of squares around the fit equals 0 because you can always draw a straight line to connect any 2 points. What this means is when we calculate r squared by plugging the numbers in, we're going to get 100%. 100% is a great number. We've explained all the variation, but any 2 random points will give us the exact same thing. It doesn't actually mean anything. We need a way to determine if the r squared value is statistically significant. We need a p-value. Before we calculate the p-value, let's review the main concepts behind r squared one last time. The general equation for r squared is the variance around the mean minus the variance around the fit divided by the variance around the mean. In our example, this means the variation in the mouse size minus the variation after taking weight into account divided by the variation in mouse size. In other words, r squared equals the variation in mouse size explained by weight divided by the variation in mouse size without taking weight into account. In this particular example, r squared equals 0.6, meaning we saw a 60% reduction in variation once we took mouse weight into account. Now that we have a thorough understanding of the ideas behind r squared, let's talk about the main ideas behind calculating a p-value for it. The p-value for r squared comes from something called f. F is equal to the variation in mouse size explained by weight divided by the variation in mouse size not explained by weight. The numerators for r squared and for f are the same. That is to say, it's the reduction in variance when we take the weight into account. The denominator is a little different. These dotted lines, the residuals, represent the variation that remains after fitting the line. This is the variation that is not explained by weight. So together, we have the variation in mouse size explained by weight divided by the variation in mouse size not explained by weight. Now let's look at the underlying mathematics. Just as a reminder, here's the equation. equation for r squared. This is the general equation that will tell us if r squared is significant. The meat of these two equations are very similar and rely on the same sums of squares. Like we said before, the numerators are the same. In our mouse size and weight example, The numerator is the variation in mouse size explained by weight. And the sum of squares around the fit is just the residuals squared and summed up around the fitted line. That will tell us if r squared is significant. The meat of these two equations are very similar and rely on the same sums of squares. Like we said before, the numerators are the same. In our mouse size and weight example, the numerator is the variation in mouse size explained by weight. And the sum of squares around the fit is just the residuals squared and summed up around the fitted line. So that's the variation that the fit does not explain. These numbers over here are the degrees of freedom. They turn the sums of squares into variances. I'm going to dedicate a whole stat quest to degrees of freedom. But for now, let's see if we can get an intuitive feel for what they're doing here. Let's start with these. P_fit is the number of parameters in the fit line. Here's the equation for the fit line in a general format. We just have the y-intercept plus the slope times x. The y-intercept and the slope are two separate parameters. That means p_fit equals 2. P_mean is the number of parameters in the mean line. In general, that equation is y equals the y-intercept. That's what gives us a horizontal line that cuts through the data. In this case, the y-intercept is the mean value. This equation just has one parameter. Thus, p_mean equals 1. Both equations have a parameter for the y-intercept. However, the fit line has one extra parameter, the slope. In our example, this slope is the relationship between weight and size. In this example, p_fit minus p_mean equals 2 minus 1, which equals 1. The fit has one extra parameter, mouse weight. Thus, the numerator is the variance explained by the extra parameter. In our example, that's the variance in mouse size explained by mouse weight. If we had used mouse weight and tail length to explain variation in size, then we would end up with an equation that had 3 parameters and p_fit would equal 3. Thus, p_fit minus p_mean would equal 3 minus 1, which equals 2. Now the fit has 2 extra parameters, mouse weight and tail length. With the fancier equation for the fit, the numerator is the variance in mouse size explained by mouse weight and tail length. Now let's talk about the denominator for our equation for f. The denominator is the variation in mouse size not explained by the fit. That is to say, it's the sum of squares of the residuals that remain after we fit our new line to the data. Y divides sum of squares fit by n minus p_fit instead of just n. Intuitively, the more parameters you have in your equation, the more data you need to estimate them. For example, you only need 2 points to estimate a line, but you need 3 points to estimate a plane. If the fit is good, then the variation explained by the extra parameters in the fit will be a large number, and the variation not explained by the extra parameters in the fit will be a small number. That makes f a really large number. Now, that question we've all been dying to know the answer to, how do we turn this number into a p-value? Conceptually, generate a set of random data. Calculate the mean and the sum of squares around the mean. Calculate the fit and the sum of squares around the fit. Now plug all those values into our equation for f, and that will give us a number. In this case, that number is 2. Now plot that number in a histogram. Now generate another set of random data. Calculate the mean and the sum of squares, and in this histogram. And we just keep generating more and more random data sets, calculating the sums of squares, plugging them into our equation for f, and plotting the results on our histogram. Now, imagine we did that hundreds, if not millions of times. When we're all done with our random data sets, we return to our original data set. We then plug the numbers into our equation for f. In this case, we got f equals 6. The p-value is the number of more extreme values divided by all of the values. So in this case, we have the value at f equals 6 and the value at f equals 7 divided by all the other randomizations that we created originally. If this concept is confusing to you, I have a stat quest that explains p-values, so check that one out. Bam! You can approximate the histogram with a line. In practice, rather than generating tons of random data sets, people use the line to calculate the p-value. Here's an example of one standard F distribution that people use to calculate p-values. The degrees of freedom determine the shape. The red line represents another standard F distribution that people use to calculate p-values. In this case, the sample size used to draw the red line is smaller than the sample size used to draw the blue line. Notice that when n minus p fit equals 10, the distribution tapers off faster. This means that the p-value will be smaller when there are more samples relative to the number of parameters in the fit equation. Triple bam! Hooray! We finally got our p-value. Now let's review the main ideas. Given some data that you think are related, linear regression quantifies the relationship in the data. This is r squared. This needs to be large. It also determines how reliable that relationship is. This is the p-value. That we calculated with f. This needs to be small. You need both to have an interesting result. Hooray! Stat. Quest. Stat. Quest. Stat Quest! Stat Quest! StatQuest is brought to you by the friendly people in the genetics department at the University of North Carolina at Chapel Hill. Hello, and welcome to StatQuest. In this video, we're going to talk about R squared. R squared is a metric of correlation that is easy to compute and intuitive to interpret. Most of us are already familiar with correlation and the standard metric of it, plain old R. Correlation values that are close to 1 or -1 are good and tell you that two quantitative variables, for example weight and size, are strongly related. Correlation values close to 0 are lame. Some of you may be asking, why should we care about R squared? We already have regular R. Some of you might just be asking, what is R squared? R squared is very similar to its hipper cousin, R, but interpretation is easier. For example, it's not obvious that when R equals 0.7, that's twice as good a correlation as when R equals 0.5. However, R squared equals 0.7 is what it looks like. It's 1.4 times as good as R squared equals 0.5. The other thing that I like about R squared is that it's easy and intuitive to calculate. Let's start with an example. Here, we're plotting mouse weight on the y-axis with high weights towards the top and low weights towards the bottom, and mouse identification numbers on the x-axis with ID numbers 1 through 7. We can calculate the mean or average of the mouse weights and plot it as a line that spans the graph. We can calculate the variation of the data around this mean as the sum of the squared differences of the weight for each mouse eye, where eye is an individual mouse represented by a red dot, and the mean. The difference between each data point is squared so that the points below the mean don't cancel out the points above the mean. Now, what if instead of ordering our mice by their identification number, we ordered them by their size? Instead of using identification number on the x-axis, we have mouse size, with the smallest size on the left side and the largest size on the right side. All we have done is reorder the data on the x-axis. The mean and variation are the exact same as before. Here, we show the mean again as a black bar that spans the graph in the exact same location as it was before. Also, the distances between the dots and the line have not changed, just the order of the dots. Here's a question for you. Given that we know an individual mouse's size, is the mean or average weight the best way to predict that individual mouse's weight? Well, the answer is no. We can do way better. All we have to do is fit a line to the data. Now we can predict weight with our line. You tell me you have a large mouse, I can look at my line and make a good guess about the weight. Here's another question. Does the blue line that we just drew fit the data better than the mean? If so, how much better? By eye, it looks like the blue line fits the data better than the mean. How do we quantify that difference? R squared. In the bottom of the graph, I've drawn the equation for R squared. We're going to walk through it one step at a time. The first part of the equation is just the variation around the mean. We already calculated that. It's just the sum of the squared differences of the actual data values from the mean. The second part of the equation is the variation around our new blue line. This is calculated in a very similar way. Here, we just want the sum of the squared differences between the actual data points and our new blue line. The numerator, which is the difference between the variation around the mean and the variation around the blue line, is then divided by the variation around the mean. This makes R squared range from 0 to 1 because the variation around the line will never be greater than the variation around the mean, and it will never be less than 0. This division also makes R squared a percentage, and we'll talk more about that in just a second. Now, we'll walk through an example where we calculate things one step at a time. First, we'll start with the variation around the mean. In this case, now, we'll walk through an example where we calculate things one step at a time. First, we'll start with the variation around the mean. In this case, that equals 32. The variation around the blue line is only 6, which is what we suspected since it appears to fit the data much better. Once we've calculated the variation around the mean and the variation around our blue line, we can plug these values in to our formula for R squared. After plugging in our values, we get R squared equals 32 minus 6 over 32. After subtracting 6 from 32, we get 26. Doing the division, 26 divided by 32 gives us 0.81, or 81%. This means that there is 81% less variation around the line than the mean. In other words, the size-weight relationship accounts for 81% of the total variation. This means that most of the variation in the data is explained by the size-weight relationship. Here's another example. In this example, we're comparing two possibly uncorrelated variables. On the y-axis, we have mouse weight again, but on the x-axis, we now have time spent sniffing a rock. Like before, we calculate the variation around the mean, and just like before, we got 32. However, this time when we calculated the variation around the blue line, we got a much larger value, 30. Now, we just plug those values into our formula for r squared. By doing the math, we see that r squared equals 0.06, or 6%. Thus, there is only 6% less variation around the line than the mean. In other words, the sniff-weight relationship accounts for only 6% of the total variation. This means that hardly any of the variation in the data is explained by the sniff-weight relationship. Now, when someone says, the statistically significant r squared was 0.9, you can think to yourself, very good. The relationship between the two variables explains 90% of the variation in the data. And when someone else says, the statistically significant r squared was 0.01, you can think to yourself, dag, who cares if that relationship is significant? It only accounts for 1% of the variation in the data. Something else must explain the remaining 99%. What about plain old r? How is it related to r squared? R squared is just the square of r. Now, when someone says the statistically significant r was 0.9, and we're talking about just plain old r, you can think to yourself, 0.9 times 0.9 equals 0.81. Very good. The relationship between the two variables explains 81% of the variation in the data. And when someone else says the statistically significant r, that's plain old r, was 0.5, you can think to yourself, 0.5 times 0.5 equals 0.25. The relationship accounts for 25% of the variation in the data. That's good if there are a million other things accounting for the remaining 75%, and bad if there's only one thing. I like r squared more than just plain old r because it's easier to interpret. Here's an example. How much better is r equals 0.7 than r equals 0.5? Well, if we convert those numbers to r squared, we see that when r squared equals 0.7 squared, it actually equals 0.5, which means 50% of the original variation is explained by the relationship. When r squared equals 0.5 squared, which equals 0.25, we see that only 25% of the original variation is explained by the relationship. With r squared, it's easy to see that the first correlation is twice as good as the second. Explaining 50% of the original variation is twice as good as only explaining 25% of the original variation. That said, r squared does not indicate the direction of the correlation because squared numbers are never negative. If the direction of the correlation isn't obvious, you can say the two variables were positively or negatively correlated with r squared equals ... whatever that value may be. These are the two main ideas for r squared. R squared is the percentage of variation explained by the relationship between two variables, and also, if someone gives you a value for plain old r, just square it in your head. You'll understand what's going on a whole lot better. We've reached the end of our stat quest. Tune in next time for an exciting adventure into the land of statistics. I promise you, I have lots and lots of slides that talk today, but these are the three most important concepts behind linear regression. In the StatQuest, fitting a line to data, we talked about fitting a line to data. Duh. But let's do a quick review. I'm going to introduce some new terms in StatQuest. Took a box for each distance, and then add line to table numbers, etc., etc., etc. We rotate just sum of. We have the sum of squared residuals on the more details. Fitting is the one with the. This is our least squares rotation superimposed on the original data. Bang squared. Here's the. A y. The slope is not 0. It means that knowing a mouse's weight will help us make a guess about that mouse's size. How good is that guess? Calculating r squared is the first step in determining how good that guess will be. The StatQuest, r squared explained, talk quick. Okay, I've just shifted all the data points to the y-axis to residual mean for sums around the very end 9. The shorthand notation around our squares mean square is the line length of the for each of the words coming. Let's step back a little. Less residual minus the variation around the fit divided by the variation around the mean. Let's look at an example. In the number points, when we take into calculate the square here means you can make a perfect prediction is this on the 100% of the variation. In this case, knowing one with because each of the in this case percent varying, we collapse in this case onto the y-axis just to emphasize the fact that we were ignoring mouse weight around that. In this example, y at 60 to the mean, then measure, square, and sum the distance from the data to the complicated equation squared. Imagine we wanted to know we want 2.5. Here's all the data in the graph. The larger tail represents fit. Since we have the x-plane, these squares adapt this tail length for add them up length with any small row. In this case, parameters with plus flip stuff 0 frowny we square mean. In this case, that would be 10. Then we'd calculate the sum of squares around the fit. 0 n number. Exact same thing. Determine if the r squared value is statistically significant. Let's review the variance around the fit divided by the variance mouse size minus the variation after taking weight into account divided by the variation in mouse size out taking weight into account 4.6, meaning we saw a 60%. Now that we have a thorough ideas r squared, combination in mouse size explained by weight are the when we take remained by explained by weight. Just as a reminder, here's the equation for r squared. This is the general equation that will tell us if r squared is significant. The meat of these two equations are very similar and rely on the same sums of squares. Like we said, by residual are the differences, but for number in a that a intercept fit the diameter. I'll split 3p2. Now the fit has 2 with now let's the fit individuals. Y divide sum of squares fit by n is good. For example, you only need 2 points to estimate a line. It is good. Then the variation explained by the extra parameters in the parameter. How to generate a set of to a p-value. Calculate into our is to create another set of random data. Relative to the number of parameters in the fit equation. People use to calculate p line that the p-value will be smaller when there are more samples relative to the number of parameters. We've given some data that relationship in the data. This is r squared. That relation. This
What is degrees of freedom? Degrees of freedom is a term most often used in statistics classes. I remember I first encountered the term in my Intro to Stats in psychology class, and I remember quite vividly my prof, he had quite a hard time trying to explain it to us. I mean, he pretty much introduced us to the formula, and he had a brief explanation of it, but it wasn't really clear, and it took me a while to kind of just wrap my head around it. Maybe I'll just write it down here. Degrees of freedom. And it's a pretty important term, I'd say, because it's used in a lot of different calculations. And although people might find it easy to calculate, it kind of helps to understand what it is, like what it's trying to say, because sometimes maybe if you forget a formula, sometimes having the pieces to it, so like the degrees of freedom might be a piece within the equation. Understanding the pieces might actually help you build the puzzle of the equation, right? I know that's helped me a few times in some of my classes. So the symbol used for degrees of freedom is df. That's really the only symbol I've ever seen used. Sometimes you see dots in between them. They all just say the same thing. So the best way to probably explain what degrees of freedom is to maybe use an example, because, well, the formal definition of degrees of freedom is, I don't even remember, it's basically just the amount of values within a system that are free to vary. So what does that mean? So it's not a very clear definition. So I'll explain it with an example. So say, for example, you have a distribution of numbers. So I love using distributions. So 3 numbers. They could be anything. I mean, it could be the number of apples people have. Like, maybe 3 groups of people. So one person has 5 apples, one has 10, one has 15. So the average number of apples for those 3 people, the mean is 10. And so let's say we want to figure out how much each person deviates from the mean. So it's basically like the variance. So what you would do is you would go minus 10 because that's minus the mean. So he's units from the system. That is they are looking from those numbers. It's minus, and so this last number can't be anything. It can't free to vary because it has to equal this last term, which is 0. So because it's not free to vary, that is not included within your degrees of freedom. So therefore, well, maybe I'll just use, it's 5, right? So vary numbers is equal to 2. Like another way I could possibly explain it is those 2 numbers you can assign any arbitrary values. In this case, they weren't arbitrary because to any so the general equation numbers, all of them has to equal vary. So I hope that helped you a little bit. Thanks for watching.
What? Still searching YouTube for math help? Are the videos from 2006 really helping? Aren't you tired of finding videos that aren't getting you anywhere in math class?
Hi, I'm Adrienne Hill, and welcome back to Crash Course Statistics. It's great to have a lot of choices, but sometimes we limit our choices in order to do something productive or meaningful, like being on a team project that needs a writer, director, host, camera person, and boom mic holder. If we have 5 different people who can be on that team, after assigning 4 of them positions, the last person doesn't have any freedom to choose theirs. It has effectively been assigned. If she's willing to give up the freedom to have a choice of positions and take on the great feat of upper body strength that is holding a boom mic, then there's a team that can complete the project. This can happen in statistics too. Occasionally, we have to give up some freedom, degrees of freedom, in order to do something useful with our data. Degrees of freedom are the number of independent pieces of information we have, and degrees of freedom are an important part of many of the models that we use. In fact, we've also been leaving out another important component of the t-test, effect size. Knowing what degrees of freedom and effect size are and why they matter will give our t-tests better context. In the last few episodes, we've covered the general formula for test statistics, and we've gotten pretty good at calculating t-statistics for all sorts of situations. Means, proportions, one sample, two sample, paired, unpaired, but every time we've needed a p-value, we've let the computer do the work, which is what we'll continue to do. But it's important to know that we're not using the same t-distribution every single time. As we've previously discussed, the t-distribution is like the z-distribution, but it has fatter tails, meaning that extreme t-values tend to be slightly more likely. And that's because we don't know the population standard deviation when we calculate a t-statistic, so we estimate it using the sample standard deviation. This little bit of uncertainty means that we don't have a perfect normal or a z-distribution. We're better able to estimate population parameters like the mean and standard deviation. Our sample size gets bigger, we're less and less uncertain about our estimate, and the t-distribution will get closer and closer to z. More information usually means we have a more accurate estimate. Degrees of freedom can help us measure that accuracy. We choose our t-distribution based on the numbers of degrees of freedom that we have. Degrees of freedom are the number of pieces of independent information in our data. Let's go to the thought bubble. After dinner with two friends, you all pull out your credit cards to split the bill. Your friend Carmen, who's a bit of a math savant and a bit of a show-off, notices that if you took your credit card numbers as a single 16-digit number, the mean of your three credit card numbers is 4551 9681 7590. Numbers is a single 16-digit number. A show-off notices that if you took your credit card numbers as a single 16-digit number, the mean of your three credit card numbers is 4551 9681 7590 9146. She said this really loudly, and you're a little nervous that an identity thief might have been lurking nearby and overheard Carmen make her very public declaration. But there's nothing to worry about. Even though a potential thief has the mean of your credit card numbers, they're not going to be able to figure out what any of your individual numbers are. In other words, there's a lot of freedom around what those numbers could be. And actually, you'd even be okay if the thief found out Carmen's credit card number. At that point, they could figure out the sum or mean of your and your other friend Eli's cards, but they still couldn't tell what your exact number was. There's still freedom for your credit card number to take on different values. It could be any of these. But as soon as someone knows the mean of all three cards, Carmen's number and Eli's number, they're going to know exactly what your credit card number is. It's no longer free to take on different values. If Carmen's number is this and Eli's number is this, then knowing the mean allows anyone to figure out that your number must be this. So you should probably make sure that Eli keeps his number under wraps, just to be safe. Thanks, Thought Bubble. In that example, the three credit card numbers already existed before we started doing any math, and they are three independent pieces of information. Eli's credit card number has no effect on your credit card number, which has no effect on Carmen's, and so on. But as soon as Carmen calculated the mean, she used up one of those independent pieces of information. Once the thief knows the mean, they only need two pieces of independent information, that is n-1 pieces. In this case, once they knew any two of the credit card numbers and the mean, they know all three. So when they learn Carmen's number and Eli's number, suddenly those numbers can reveal yours. The thief can figure out your exact credit card number since it's no longer independent of the others. To bring it back to our t-tests, when we calculate a mean, we're using up 1 degree of freedom or one piece of independent information. The amount of information that we originally have depends on our sample size n, which is why you'll often see it in the formulas to calculate degrees of freedom. The more data you have, the more independent information that you have. But every time you make a calculation like a mean, you're using up one piece of independent information. So for example, we have data from 100 randomly sampled square miles of avocado orchard, and we've painstakingly counted the number of bees spotted in each sampled square mile over the course of a week. The bee population is declining. We need to be sure our avocados are getting pollinated. The owner of one avocado orchard says that she usually sees 15,000 bees per square mile. So you set out to analyze your data to see whether you think the bee population has changed. You have 100 pieces of independent data, one measure from each square mile. So when you calculate the mean number of bees from all 100 square miles, you're using up 1 degree of freedom. Now that we know the mean number of bees is 16,838, you only need 99 of the bee counts to figure out what the count for the 100th square mile would be. With a quick one-sample t-test, we get our p-value from a t-distribution with 99 degrees of freedom. If we had less data, say 6 data points, we'd only have 5 degrees of freedom, which will give us a slightly different t-distribution with fatter tails.